So, hello everyone. Good morning. So, again, my name is Sergey Kholkin. As we yesterday, I will be supporting the lecture of Alexander by a corresponding seminar for beach matching in this mini generative modeling course. And yeah, so we will go again through some parts of the theory that Alexander has told today. We will take a look at both several algorithms that Alexander has explained. For instance, the beach matching and unconditional beach matching. We will implement them, and we will implement them on two cases. First is very small two-dimensional case to see the exact difference between conditional and unconditional batch matching. And then we will go to the more scalable, more practical case, which is actually quite practical in real life, is solving the image inverse translation problems via batch matching. And overall, so yesterday's seminar was dedicated to the flow matching and the general coupling. And today's seminar will be mostly dedicated to the batch matching with an emphasis on difference between conditional and unconditional batch matching models. So I think you also have a notebook, right? Which also, as yesterday, has some empty spaces in it. They are marked, if you try to run the code, you will get an error. I will in particular implement them in this seminar, and you could do it by yourself. Just read the theory before the cell with empty space, and just implement the part of the function that you need to implement. And after the seminar, I will, of course, give you the full solved notebook with all the empty spaces filled by correct answers. Alexander's lecture was quite extensive and quite general, and I will recap several parts of it. So first, we will recap what diffusion bridges are in particular. So again, at the center of bridge matching models, there are this prior process, right? Which is this diffusion process with its own drift and volatility coefficient. And with some distribution of it. And it can be any general process, but in our case, in particular, it would be just a Brownian motion. So next.
One thing to interrupt, take a look at the camera and wave your hand. Done. Yeah?
Yeah, great. We have this prior process Q, right? And then what do we want? We want to take 2 points and condition this prior process Q to start at one point and end at another point. So what we do here is we apply this Dubas transform, which employs the information on the ending point of the diffusion process, right? This gradient of logarithm of our Q, which is the density of our prior process, right? So we just modified the drift of our diffusion process a little bit, and as you can see, this process is actually non-Markovian anymore, right? Because we have a conditioning on the future point, which is xt and is there in the drift. So this process is non-Markovian, and since it is non-Markovian, to sample from it, we actually need to know the xt point, and if we don't know it, then we cannot sample it, and this is a particular generative modeling task when we don't know the end of translation. So unfortunately, we cannot use this particular process for sampling, but we will find a way to actually make it work. And so Alexander said, if we have a mixture of such diffusion-based processes, which we do just weight by two distributions, P0 and P1 and their corresponding coupling P, then we get this mixture of reciprocal processes, right? So it looks like this. For each two particular points, x0 and xt, we draw this diffusion bridge between them. And in contrast with flow matching, there are several diffusion bridges that we can draw, right? So in the flow matching case, we had, again, these 2 points, x0 and xt, but we had a linear interpolation between them. But now we do have another interpolation, which also adds noise. Hence, there are several of them for each noise implementation. And so if you have points, as in flow matching, of course, if you have point in distribution P0, you have distribution Pt, you have points from those distributions, and you have joint distribution between those 2 points. Then you just sample points from those from the joint distribution and build a bridge between them. Just like in case of a flow matching, but with some additional noise. And we call this a reciprocal process. And in this particular, so like all the theory that was previously was mostly general for the general stochastic processes. However, in most of the cases, the most popular case is the Brownian motion one, because it is the simplest one, and actually it reduces to the flow matching in the case of zero volatility. So in the case of Brownian motion, our process will look like this. Yeah. When we do not have the drift is equal to 0, and the volatility is static and is predefined. And the final T for our process is T equal to 1. And yeah, of course, then we also need to compute the Dubas transform to perform diffusion bridges. And it has this very simple form of x1 minus xt divided by 1 minus t. Which is also quite similar to the flow matching one when we had x1 minus x0. So yeah, it looks like this. So now I will visualize it. In the case of two-dimensional Gaussians, yeah, let me run it. And yeah, so this is our data that we'll be working for the first part of the seminar, which is, so we have two Gaussians as a blue distribution, and we have two Gaussians as a red distribution. And we will build a bridge model to transport the blue distribution into a red distribution. In contrast to the previous flow matching seminar, when we had the first distribution is just a Gaussian, and the second distribution would be a mixture of Gaussians, which was generally just usual generation from noise problem. Here it is more of a domain transfer problem, because we have both distributions and source and target which are non-trivial. And so let's take a look at our Brownian bridge trajectories. Yeah, here they. Yeah. So this is our Brownian bridge trajectories. So yeah, what's happening here? So first of all, here are 3 plots, each one for different volatility coefficient, right? So it is like obvious that the lower the volatility coefficient, then yeah, of course, the less noise we have in our trajectories. The higher the volatility coefficient, the higher noise we have in our trajectories. And yeah, as you can see in the first 2 images, I think the volatility is more or less controllable, but in the third case, the volatility is yeah, not controllable anymore. So one of the tasks that you have to solve if you actually implement the bridge matching model is the choice of volatility coefficient. And actually different problems require different volatility coefficients, but the epsilon equal to 1 is considered as kind of a golden standard for the bridge matching model, and that's one that you start with. And so we will further implement the bridge matching models mostly with coefficient equal to 1. And yeah, so again, we have like these points and a diffusion bridge between them. So in the case of flow matching, we will have to put the flow matching here. It will be just a linear interpolation between green and yellow points. So if we have pairs between source and target distribution, then we can easily just build the diffusion bridges between those 2 points. However, as I said, this process is non-Markovian and we cannot generate data from it. So that's the problem because, again, the task that we solve is the data generation, right? And we cannot employ reciprocal processes for it. Then what we can do is we can recap that we can do a Markovian projection or a bridge matching that Alexander told about in the lecture. So, and in particular, implement forward in time bridge matching. So what it basically does in 2 words, we take this reciprocal process that we have here on each of these plots, and we find closest to it Markovian process or stochastic differential equation in our case. So closest is kind of weak term, but we look at it as a closest in Kyle divergence term. So how do we find this stochastic differential equation that is the most closest to our reciprocal processes that we drew in the previous plots? Actually, it appears that it is quite simple. All that we have to do is to take the reciprocal process equation, right, which is drawn right here, this one, which is, again, non-Markovian, and just add an expectation over the second term, which has the non-Markovian input into it, this log gradient of Q, also known as the score function. We just have to implement the expectation over it. And the final expression would look like this, right? So it is just the same as a diffusion bridge. However, we just take an expectation. And yeah, that's it. However, this expectation is actually intractable. But what can we do? We can actually learn it. Though it is intractable, it can be explained as a solution to the optimization problem. Optimization problem is written right here. This is, again, very similar to the flow matching optimization problem when we also learned this drift U. And we had a target of not this complex gradient of logarithm, also known as Dubach transform function, but just difference between x1 and x0. Again, our things are very similar to the flow matching. We also have this time. We also have this point sampled from the joint distribution, and we also have this intermediate point, which in the flow matching case was just linear interpolation between 2 points. However, here it is a linear interpolation plus some noise on top. Yeah, so in our particular seminar case, we use the less general form of a Brownian bridge prior process, and hence we can just substitute the Dubach transform function expression that we defined previously, which is this one, xy minus xt divided by y minus t. All the expectations are in place, of course, but after that, the optimization problem will look like this in more simplified form, which is quite evident now that is very, very similar to the flow matching, because flow matching just has the different, slightly different target in this regression problem. Yeah, so this procedure is called bridge matching. And as I said, this seminar will be mostly dedicated to the comparison of conditional bridge matching with respect to just bridge matching and conditional one. And the only difference of unconditional bridge matching with respect to the conditional bridge matching is just the addition of x0 to our drift function of our stochastic differential equation that we learn in our optimization problem. Despite those two optimization problems look very, very similar, the addition of such term, which is basically a non-Markovian term of dependence of a drift function on the start of the translation, it actually changes things a lot. Now we do not learn in particular let's say, closest the static differential equation to our reciprocal processes. However, we learn just our reciprocal process just by in Markovian form. Yeah, Markovian conditioned on the start. And it will change the behavior of our diffusion trajectories that I will show later. Yeah, can be seen both as a plus and a minus depending on the particular task that you solve. So a little bit of visualization. So what do we start with? We start from this reciprocal process, right, which is just collection of points with Brownian bridges drawn between them. And then we apply this Markovian projection to find a stochastic differential equation that is the closest to the reciprocal process on the left. While we cannot sample from the process that is defined on the left, we can sample from a stochastic differential equation that we have learned on the right. So this is a particular generative model with stochastic differential equation that we can actually inference just as in regular diffusion model. In comparison to the regular diffusion models, we can start from arbitrary distribution P0, which regular diffusion models cannot. Yeah, so again, we just define the pairings between samples from distribution P0 and distribution PT, P1, and then just solve the simple regression optimization problem. Very simple, very close to flow matching, yeah, very simple to implement as well. So here we'll go to the implementation. So yeah, this theoretical part again is not very easy to understand, quite heavy. So if you have some questions, I can answer them now, so it will be easier for us later. Yeah.
Trajectory is the same. Am I right that the noise level on every point of the wall trajectory will be the same, or it will bigger in the middle, smaller when we go towards x0 or x1, or like that?
Yeah. So it depends on particular how do you ask the question. So we start from this. We choose as a prior process this Brownian bridge, right? Which is Brownian motion, which is right here. When the stochastic coefficient is static, right? So if you just go with it, then you will have a static epsilon coefficient, and noise everywhere would be equal. That is one point. However, when you do and imply this diffusion bridge, yeah, you also have the static volatility coefficient, yeah, which would be again just epsilon. However, yes, you can see that it actually ends at a point where you have no noise, right? That is because our Dubas transform function, where is it? Yeah, right here, it just pushes all the diffusion trajectories into one point. Yeah, we still have a noise at the end, but it is being cancelled by the Dubas transform function. Yeah, so considering the case wherever noise is static or not, we will later implement a particular way to draw samples for our training of our model, and there indeed we have zero volatility on the points, and we grow in quadratic form volatility to the center. Yeah, now I hope it's more or less clear. Yeah, and I think we'll be more clear when we go to the particular implementation of particular parts of our model. And again, so in the notebook that you have this empty space with a code, then you can implement yourself, and that I will implement right now. So this in particular is loss function, and in our case, this loss function is very, very simple. We just have our drift function and regress it with respect to this very, very simple regression term, right? And so if we want to implement it, what do we do? So first, we write torch norm. It should be our loss function. And inside the torch norm, we just have this xc hat, which is our drift function that we have already evaluated. And I have this xc hat minus, which is also known, which is target. And target, again, you can see it is very, very simple target, which is just x1 minus xt divided by 1 minus t. Also, can you see a little bit of a computational problem in this computational objective? Yeah, I mean, if t is close to 1, or yeah. That is actually a problem. That's why in most of the implementation cases, you have this small epsilon. We do not go in particular to the end till the 1. We go till 1 minus epsilon, which can be like 10 to the power of minus 5 or like another way small number. Yeah. Yeah, so we have this target, and we also want to shape it a little bit before making the, because we can also work with images here. It will be evident why do we need this a little bit later. Yeah, I think that's it, right? Yeah. Yeah, so like this part is very similar to the flow matching. Yeah, except for this T part, which you don't have in flow matching. So next, for our, in particular, training procedure, the main things that we have to implement is target and sampling of xt points in the middle of our trajectories. So remember that we have these points, x0 and xt, and we want to sample a point somewhere on the Brownian bridge trajectory in between. And like previously in flow matching, was just linear interpolation, so we just taken one x0 multiplied by t, taken xt multiplied by y minus t, and here it will be quite similar. So here's the function of for implementation. Yeah, and of course it is like written right here, and here it is this parabolic coefficient for the volatility. Yeah, so we still will have this linear interpolation term, which would be just x0 multiplied by t, 1 minus t, plus x1 point multiplied by t. However, we will add a noise coefficient z multiplied by our, it's already implemented, our standard deviation, which would be a parabolic function of t multiplied by our volatility coefficient. And yeah, that's the way to sample the points from between these trajectories. Awesome. Then actually we have everything that is set for the training. And however, yeah, so we have gone through the training, but later we would need to actually inference our model, right? And while in the flow matching case, we have used ODE solvers, right, from these two libraries, which were torch-din and torch-defect. However, we cannot use ordinary differential equations for the inference of bridge matching models, at least not in our particular case. In general, you can, but in our particular case, you cannot. So we would have to write a stochastic differential equation simulation solver. And there are actually not a lot of solvers available for stochastic differential equations, and we will implement the simplest one that I think that everyone uses, which is also known as Euler-Maruyama solver. And yeah, you can see why it is called Euler, because it is just Euler solver for the ordinary differential equations with an additional noise term. And yeah, so here's the function for its implementation. So again, xt would be just, yeah, let's implement it, just implement it. So first of all, the next xt point would be just another xt plus some drift term and some volatility term, right? Plus drift term and volatility term. So the first, let's start from volatility term, which would be square root of delta t multiplied by epsilon multiplied by some random stochastic noise. So we have our random stochastic noise somewhere here. No, we don't. Okay, so as previously, we have the z, which is our volatility coefficient, or our noise term, and standard derivation, which is just a square root of delta t, which is in our case Euler dt, multiplied by epsilon. It's yeah, multiplied by epsilon, and the mean would be just the drift term that we have as an output of our neural network, which is called here drift predict, multiplied by the delta t, which is the accuracy of our solver. Yeah, it's again dt, right? Yeah, and we haven't defined z, which is just sample from random noise distribution. Yeah, I think that's it. Yep. Yep. Great. So, and now I think we are through with the implementation part, and we can do a combined overall class for solving for building the bitmatching generative model. So if you have some questions with respect to the implementation, yeah, maybe you can ask them. Or, you know, everything is, yeah. Volatility this term. So, yeah, so implement this Euler-Mayama solver, right? Where this volatility term is this one, which is also you can call as a noise term. So yeah, this is basically an Euler ODE solver with an addition of this noise, right? So in terms of implementation, it is also like could be evident. If we will just comment out the volatility term, it would be just only a differential equation solver, right? Yeah. No, it's a standard derivation, like yeah, this term, which is before z, under square root 1. Yeah. So you can actually also view the one step of Euler-Mayama solver as sampling from a Gaussian distribution with a mean of this f multiplied by delta t, and with this volatility. Yeah, with this standard derivation, sorry. Yeah. 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 Yes, we can. However, what's this like? Why it is possible in regular diffusion models, right? When you have this just stochastic differential equation, and then you can transform it via Fokker-Planck into a probability flow ODE, right? And yeah, use ODE solver, and I think that's how most of the diffusion models actually work at the end, because this solver is actually due to the stochastic term, it's not very nice in practice. And yes, so here we also can do this. However, in the regular diffusion models, why can you do this? Because you build a backward differential, stochastic differential equation, right? And you already have a forward one, which is closed form. So in here, in bridge matching model, we only build the forward and we don't know the backward. So if we knew both of them, we can actually do just by learning two bridge matching models, we can combine them and make one ODE solver. Yes, but if we build only one diffusion model, then we don't have another pairing forward to backward process, and we cannot construct a probability flow ODE, unfortunately. But you can, yeah, you can actually do it. However, like in practice, I would say that is not very much. ODE solver is not very nice for the bridge matching model. I will maybe like add a little bit of a comment for it in the image generation case, where it's like actually would be, if you do it in practice, it will be quite evident that it doesn't work on the image generation case, which is the most of the applications of a bridge matching actually. But yeah, it's totally possible. Yeah. Okay, if everything is understandable with this implementation, and maybe you have done it yourself, then we can go to the whole bridge matching class implementation, which would just combine all the things that we have done until now. So what this class is, again, similar to the bridge flow matching class that we had in the previous seminar. We had a neural network here, which also receives an xt point from the bridge matching trajectory, and outputs drift estimation, which also has the same notation. Yeah, and also it inputs receives a time embedding. We have epsilon, which is the volatility coefficient, which can be tuned for the particular task, and we have this flag, which is for either conditional or unconditional model, and it will mostly just control the input to the neural network wherever do we have x0 as the start of the generation as an input, or we don't. So here we have a function for sampling of middle points from our diffusion bridge trajectory that we have implemented previously with a particular epsilon coefficient. So this is different for different epsilon coefficients, of course. Then we have a train step function, which receives a pair from our ground truth distribution. Receives also, it also receives time. Yeah, it also receives time when we do want to particular train our model. Samples points from the diffusion bridge trajectory for this particular time. Inferences the neural network. And then just it calls the loss, which is we have implemented, and which is just L2, like mean squared error loss. And then if we want to inference our model, then we can call our Euler-Mayama solver, which as in previous case, and as Alexander said, particular this case, has this parameter NFE, which is number of function evaluations, which defines the accuracy of your solver. So the more NFE you have, the more computation you throw into your generation, and the more quality would you have. The lower the NFE you have, the lower is the quality of your generation, but it will be faster with lower computational resources. So again, this is a hyperparameter for balancing. And you can train your model and only then change the number of function evaluations, just as in diffusion models. So 8, and now we have all the things implemented, and we can actually try it on a particular data, which is transferred from two Gaussian distributions to another pair of Gaussian distributions. And first, we'll start from a regular bridge matching model. So as a neural network, we will use just an MLP, but I think this time it would have actually decent time embedding module, except for the, instead of previous one that we used in flow matching seminar, which is just an additional input, but actually both of these neural networks are substitutable. And we choose volatility coefficient equal to 1, because it is, I would say, golden middle volatility coefficient that you use if you don't know in particular that you want to use some other volatility coefficient. Then train some optimizer, we add a training loop, which is very, very simple because you just go for number of gradient steps that you want. You sample your data, which is just samples from two distributions which are independently mixed. And actually, as in the previous flow matching case, there are actually different flow matching models for different input transport plans that you input to the model. So you could have here as well a mini batch optimal transport plan as for flow matching, anti-mini batch optimal transport plan, or even you can do this rectified flow procedure that in this case is called iterative diffusion batch matching or diffusion Schrodinger batch matching. You can utilize all of those things that we have tried for flow matching here. But yeah, we will go with simple independent transport plan. Yeah, so we can train our model for a little bit. Oh, there's some error. Yeah, let me fix it real quick. Yeah, I see. Yeah. So yeah, while it trains, I actually have some of the results already planted in this notebook. So this is just generation samples, and as our target is to start from a blue distribution and go to the red distribution, you can see that batch matching actually does this quite well. So the yellow samples are from our model, while the red ones are from ground truth distribution. And you can see that they are pretty much the same, except for some stochasticity that came from the fact that we have finite number of samples. So it's almost trained. And yeah, let's take a look how our in particular trained implemented right now batch matching works. And there's an error in Euler Mayama solver. Yeah, okay. Yeah, it has so this should be a touch tensor. Yeah. Yeah, the generations, it's actually interesting how in this case the generation would look like, but they would not fit the target distribution quite well, yeah. That's a good point. Yeah, now until trains, we can have a look at how this actually looks like done well. Yeah, so it looks like this. So we start from a reciprocal process at the left, right? When you have points, and we just draw a diffusion batch trajectory between them, right? And then we have learned a diffusion batch matching model, unconditional one, right? That also takes, in this particular case, this green dot and inferences a diffusion trajectory to get the yellow point. So as you can see, there are some differences between both of those, between the left and the right, because as Alexander said, actually the diffusion batch matching model, the regular one, changes the input procedure because it doesn't find exactly the same formulation as we start in reciprocal process one, but it finds the closest to it Markovian one. And that leads to some augmentations. For instance, you can see that here's a very interesting case when we have this yellow dot, right? And we inference a diffusion trajectory and it goes to the center. But then in the reciprocal process case, it just goes straight to another Gaussian, right? But here it doesn't go to this red Gaussian. It turns around and goes to another Gaussian, right? So here's the change. So if we would repeat the process on the left fully, then we will just go through the center to this Gaussian. However, we turn around and go to this Gaussian. This is the similar thing that we also can see in flow matching, which in particular makes it applicable for the unpaired domain translation, because in several words, this Gaussian, as it is closer, this red Gaussian, as it's closer to this blue Gaussian rather than the top one, closer in terms of L2 norm, it magnetizes the diffusion trajectories from our diffusion bridge. And the cyclical process doesn't. So you can see some changes here. And actually, it seems quite natural and nice that we start from the lower Gaussian and go to the closer Gaussian rather than to the farthest Gaussian, while sampling from two Gaussians perfectly at the end. Yeah, so this is augmentation by a regular diffusion bridge matching model. So I think that, yeah, okay, we'll just use already done notebook. But yeah, so you take the cyclical process, find the closest to its static differential equation, and everything is perfect. Now, however, we'll go to a conditional diffusion bridge matching case, which is rather different. Because while we just simply add an additional input to our neural network, which actually changes the neural network for a little bit, because now we have not two inputs, which is xt and time, but we have three inputs, which is xt, time, and the start of generation x0, right? So we would have to change the neural network a little bit. However, the other things are the same. So we use the same class, we use the same training procedure, the same hyperparameters, and that's it. Oh, actually have it. Yeah. So yeah, it will train for a little bit. And we use the same inference procedure as well, where just another input is fed into the neural network. And you can see that it actually learned conditional bridge matching model, also samples from our target distribution quite well. So again, these yellow samples are very much close to the red ones. And yeah, so it has some like 15 seconds till it finishes training. Yep. Perfect samples from two Gaussians. And now what is interesting here, if we will take a look at trajectories. So here we have three plots, right? And though we used the same reciprocal process as the start of our bridge matching procedure for both of the conditional and unconditional one. So yeah, you cannot see it quite well. Yeah, this would be better. So again, on the left, we have a starting reciprocal process. In the center, we have unconditional bridge matching process, which you can see even better that it doesn't want to go through the center. It goes to the center and then chooses between two Gaussians, the upper one and the lower one, and chooses the lower one because it is closer to this center. And yeah, if you go from the top one, then we go to the center and go to the top Gaussian as well because it is closer. However, in the conditional bridge matching case, which is on the right, our diffusion bridge model trajectories just go through the center quite well. And in particular, this conditional bridge matching model actually fully recovers the reciprocal process on the right. So if we will, take more samples, can we take more samples? It would be much more evident. No, we cannot take more samples in this implementation. But yeah, if we will keep on resampling, that we will see that while plots on the left and plots on the right actually look quite similar, while plot in the center is quite different. So yeah, and so the choice between conditional and unconditional batch matching mostly depends on whatever behavior you want. So if you have a perfect coupling between, for example, if you have pairs from this Gaussian that goes to this Gaussian, then you can use conditional batch matching, because then it would just represent the diffusion trajectories between one and two Gaussians. However, if you don't have meaningful transport coupling plan, as we actually have in this particular case, maybe it is better to choose the unconditional batch matching model, because it goes to the closest Gaussian rather than to the farthest one. Yeah, so choose batch matching model, either conditional or unconditional one, depending on the behavior that you want. I think that's mostly it for the first part, which is two-dimensional part. So if you have some questions regarding to batch matching models behavior. No, okay. Yeah, also I have here one more plot, which is different batch matching models for different volatility coefficients. Yeah, in this particular case, it is just unconditional batch matching model trained with 3 different volatility coefficients. So the first one, yeah, in this case that we have previously, we trained our batch matching models with volatility equal to 1. However, here on the left, we have a case with less volatility, equal 10 times less volatility. And on the right, we have a case with 10 times more volatility. And it is quite evident that diffusion trajectories on the left has less volatility than the other ones. And the trajectories on the right have more volatility than the previous ones. However, you can see that those trajectories on the right are very chaotic. Right, and this is actually not very good for the SDE simulation solver that you use, because with higher noise, because with higher volatility in your trajectories, each of the SDE simulation steps actually has more noise and induces more error in terms of discretization. So maybe for this particular case, because I think you can actually see in particular how volatile it is, because you can see that in some particular points sampled from SD, and you can see that, well, this one, it goes from here to here, right? So it goes to the left. And now we have another step from our diffusion trajectory, and it goes not to the left, but it goes on top. And then it goes like back again somewhere to the right bottom. So this actually induces a lot of errors during SD simulation. And maybe for this case, you want to discretize your SD solver with more accuracy, with more frequency, and it will induce more computational resources needed and more number of function relations that we need. In contrast to, for example, left case, where it is, I think, almost enough to do 2 steps of SD solver, one for the start, the other in the middle, and that's it. And you can pretty much sample from your model quite well, even with 2 steps from your SD solver, while on the right, you would need like 100 to 1000. As conclusion, we have 2 types of batch matching models. One is conditional, the other one is unconditional, while the first one finds the closest stochastic differential equation to our reciprocal process. However, it doesn't fully save the reciprocal process plan that we start with. So we actually change our reciprocal process due our batch matching training procedure. And in the contrast, we have conditional batch matching model, which just has an additional input to the drift function. However, it changes the output completely. And now we just basically train some stochastic differential equation model that can perfectly represent the starting reciprocal process that we have. And wherever you need the conditional or unconditional one very much depends on your particular task. And it would be also pretty much evident on the real life case that I will show right now for the image inverse problems. But yeah, in most cases, it depends on type of behavior that you want. Okay, so yeah, that was two example, but the actual implementation, practical need for the diffusion bridge matching models comes from the domain translation problems and in particular image inverse translation problems, such as, for example, images deblurring, images denoising, images super resolution, or I don't know, which ones do we have? Some more complex image restoration problems. And in this particular case, we will target deblurring on a data set of flowers in 64 by 64 resolution. Yeah, so here is some code for the data download. Right, so I think that flowers 102 data set, you can get it directly from Torch. And yeah, that would be it. And here how the samples look like. So this is data set of flowers of different colors, different types, with although quite similar background of some green leaves. But overall, nice data set for a toy image problem. However, what do we do now? We try to regress these samples, try to induce blurring to our samples. So here's the function that we use for deblurring, right? We use just pooling, two-dimensional pooling with some huge kernel size, so that our degraded samples look, very much different to the beginner ones. So basically what you can see is the color and some rough shape of the flower, but no more. And our task in this part of the seminar would be to take the lower samples and try to generate the upper samples depending on the lower samples to make so-called deblurring. Yeah, this is done perfectly by the diffusion bridge matching models. First, let's draw some epsilon trajectory. Yeah, let's go to another similar. So the other part that we have to solve is we have to choose an epsilon for our model, because it is a quite important hyperparameter, right? And we want to choose it, so it won't be that bad. So here's the diffusion bridges trajectories for different epsilon coefficients, and we start from the smallest one, which is 10 to the power of -3. And so on the left you can see blurred samples, right? And on the right you can see clean samples, and all the samples in the middle are slices from diffusion bridge trajectory. And you can see that actually you cannot see any noise on the first kind of samples. You can see that this smooth transformation from blurred image to the clean one. Then we can add a little bit more noise with epsilon of 10 to the power of -1, and you can actually see noise here. You can actually see that you do not just do linear interpolation, but you add noise in between. And of course, there are more noise in the middle of our trajectory. And noise slowly disappears when we go to the borders of our trajectory, either blurred or ground truth image. And if you take even more noise, and this epsilon equal to 10, then we get this. So I think it's quite evident that this particular case with such high volatility would not be very meaningful for our model, and it would be quite hard to learn such trajectories because while you can see some shape of flower here, or shape of those two flowers, other than that it's just almost pure random noise, and the particular image signal is just dominated by noise, which is not very good in our case. So in the image translation problems, which is, yeah, this is actually how it goes. So you do not want to use the higher epsilon coefficients because it would just kill all the image signal, but you would use rather smaller epsilon coefficients, like this, like 10 to the power of -1, 10 to the power of -3. We will in particular use the middle one, which induces some noise. However, actually in practice, I think it is considered that lower noise cases are better. So you can use not just epsilon of 10 to the power of -3, you can use epsilon 10 to the power of -5, and that will give the best results. However, you cannot degrade it to 0 because it would just diverge. This would be a flow matching case. So yeah. So yeah, we go with this middle epsilon coefficient. Yeah, question? Yes, indeed. However, like in particular this case, it would not help very much because you still learn from these samples, right? This is the input to a neural network. And no matter the number of steps that you add, the training samples will not change. So yes, if you can try to learn a neural network for this particular case with epsilon of 10, and then on the inference stage, it would help to actually induce, to get more accuracy, more time discretization to your HD solver, and it would actually, help to produce better results. However, still, this is your training samples that you would use as an input to a neural network. If they are fully noise, then still the image signal is dominated by the noise, and it would be very, very hard to learn this particular case. It would be much easier to learn the upper two cases. Yeah. Yeah, so I think now we can actually go to the particular implementation for our bridge matching. So we have the same class as we have used previously, which is just this bridge matching class with absolutely the same sampling of training samples, absolutely the same loss function, and etc. However, we have different neural network, which in our case would be a UNet, two-dimensional UNet with, again, from diffusers. I think the very similar one that we used for the flow matching case, with dedicated time embedding, and we use epsilon equal to 0.1. And first we use unconditional model. Define data set, run our model for 20 epochs. It takes actually quite some time, I think 10 minutes to train the model, so I will skip it. And we will take a look at the samples. Yeah, again, during the evaluation, we have exactly the same Euler-Maruyama procedure as we had previously, which we run with 100 discretization steps, which is, I would say, more than enough for this particular case. I think you can degrade it up to 10 and it would still work. Yeah, so this is the result, right? So to recap the target, what do we have to do? What do we want to do is to take these corrupted samples, which are blurred very much, and restore the clean samples. Yeah, you can see that our unconditional regular bridge matching actually, well, at least partly solves the problem. Because, for instance, you can see that this, well, you can see the shape of a flower and you can see the color of it, and you can generate with this information something that looks like an actual flower, right? And that's what the model does. So yeah, take a look at this case when you have a red outer rim for the flower and white center, and indeed it generates something that looks like a flower with red outer rim and red leaves and white center. And you can see the following the same for all the other cases. However, here's one problem why this is not ideal, because actually samples look kind of smudged or kind of blurry still. For example, this change here from the red, from the white center to the red outer rim is like either blurry or smudged, whatever you call it. And while it actually looks like a flower, there is something off about those samples. But I would still consider it quite decent, actually, restoration, because you cannot see very much in those corrupted samples to begin with. But now we will take a look at particular conditional batch matching, because it actually solves this problem a little bit better. So we use the same neural network, but with additional input. Just as in the previous case, everything else is the same, epsilon coefficient is the same, training procedure is the same with the same optimizer, the same number of epochs, the same gradient steps, with same batch size, with absolutely the same inference procedure, which has the same number of function evaluations, same discretization, and this is the result. You can see that it is probably a little bit better. So again, we start from the image in the middle, and we generate the image on the bottom, and we want to look at like the image on the top. And in comparison to the just regular batch matching, you can see that, for example, you have this clear boundary, right, between the center of a flower and the outer rim of the flower. In general, it seems more clear and crispy rather than the conditional batch matching one or unconditional batch matching one. And if we will take a look at the comparison between those two models, again, the training is the same, the inference is the same, everything is the same. We just have an additional input to the model. And while this one is a generation by a conditional batch matching, the bottom one is generation from unconditional batch matching. And in this particular case, you can see that there are some indeed difference, and the sample on the top looks a little bit better. Oh, also, you can see, this case where the sample on the bottom is, actually the sample from conditional batch matching is quite decent with respect to the clean one. It almost seems like it has been in a training set. However, it isn't, because it is a validation set. So on this case, you can see the difference between conditional and conditional batch matching quite well, and that in this particular case, conditional batch matching looks a little bit better because of this additional input to the model. And I think that's it for the most part of the seminar. A little bit of a conclusion about this particular experiment. In this particular, diffusion batch models are used for the image restoration a lot. And in this particular case, conditional batch matching looks a little bit better than the unconditional one. However, it is not the case always. In many cases, for instance, in image denoising, in image super resolution, we actually find that unconditional batch matching works a little bit better than the conditional one. Why? This is something that we call L2 distance prior, which is can seem a little bit weak. But for instance, if you do denoising, then you can see that since you have an image, you add a Gaussian noise to it, you can see that there is clear L2 distance prior to it. These kind of problems are better solved by unconditional batch matching, while for conditional batch matching is mostly solved for these problems such as deblurring in painting, image colorization, and some of the types of image super resolution, for instance. However, on practice, it mostly worth to take a look at both. take a look at both conditional and conditional batch matching and decide what is better. Because it very much depends on the particular task that you solve. And although I think in 70% cases, the unconditional batch matching is better, on the other 30% of cases, actually, and in particular in the Blueink one, the conditional batch matching is better. Yeah. So as a conclusion to the full seminar, yes, we have implemented regular batch matching. We have implemented conditional batch matching. You can see that this is very easy, very stable algorithm. And we take a look at the differences between conditional and unconditional batch matching. We know that while regular batch matching, it doesn't fully preserve the transport coupling that it starts with, the reciprocal process that it starts with, while conditional batch matching indeed does preserve it. And in terms of real-world applications, it is worth to try both conditional and conditional batch matching. And while conditional batch matching is good for problems such as general image-to-image translation problems, such as day-to-night translation or image colorization, the regular batch matching is very good for image inverse problems such as image denoising, image super resolution. Yeah. And another thing is that regular batch matching can be applied for the unpaired learning, as Alexander said, via inverse diffusion batch matching procedure, while conditional cannot. Yeah, so here's some additional resources. And yeah, I think that's it for the part of the seminar. If you have some questions, yeah, you can ask them. Okay, I would consider it as everything is crispy, clear, and yeah. I think you will also receive a fully filled notebook that you can run by yourself, and also you can run the image denoising problem. You can actually play a little bit with it and try, for example, different epsilon coefficient for this image inverse problem, and you can try different type of degradation. For example, you can try, so here it is implemented as a deep Blueink problem, right? Yeah, you can try different corrupt functions such as JPEG degradation or, I don't know, noising, and yeah, it will actually produce decent results. So, okay, thank you.